Right, so we're gonna now finish our discussion of buffer and titration. Now we're talking about acid-base indicator, which is an important component in titration. So remember that an indicator is the substance you add to help you recognize when you've reached a certain point in your titration, usually when you've reached the equivalence points. When we see a color change, then we know we are done with our titration. The indicator itself is usually a weak acid. It has different colors depending on when it has its proton or it doesn't have its proton. So you can imagine the generic formula of an indicator is just HA, and its conjugate base is A minus. And so this species has its own color and this species has its own color. So you're going to use that to help you determine when you've reached the appropriate point in your titration. The actual name of the time when color is changing is called the endpoint of the indicator. And so when we choose a color, we're really choosing the color of the endpoint, but we're trying to match the endpoint to the equivalence point. But right now, all I want to do is show you really quickly a list of common indicators that you might have used and where they're changing. So some of them have the same sort of color differences. So for example, here is methyl orange, a really common indicator, and methyl red. They both have sort of an orange to yellow type of conversion, except that they happen at different pH values. So how to read this table is if you're looking at methyl orange, the change in pH occur around, let's say 3.8. And so the range where the color change would occur slowly from red all the way to yellow is between around pH 3 to all the way to about 4.5. Okay, another indicator that you've used before is phenolphthalein. That's this one right here. So if you look roughly, the middle point here is about 9.2, 9.3. And then the range where there is a change in color going from colorless on this side to pink on this side is between about 8.2 all the way to about pH of 10. Okay, now we have to choose these indicator to match the pH at our equivalence point. But before we do that, we need to know when will the color change. How do we know that the color will be one color or the other color? Depends on the ratio of the acid form of the indicator versus the conjugate base form of the indicator. So here I call them HIN for the acid form and IN minus for the base form of the indicator. If we take a ratio of IN minus over HIN, we can tell what color we will see. And it just looks like this. So if the IN minus is much less than the HIN, in this case 1 to 10, so there's 10 times HIN for every one of the base, then the color we observe would be just the color of the HIN. And the color of the HIN is just the color on the left side of this chart right here. So for phenolphthalein, the color of the HIN form is colorless, whereas for something like methyl orange, the color of the HIN form would be red. What happens when the ratio is 1 to 1? That's when you have exactly the mixture of the two colors. So for phenolphthalein, there'll be a light pink color, something like this. For methyl orange, that'd be an orange color because it's a mixture of red and yellow. What happens when you have 10 times more IN minus versus HIN? Well, then you'll see the color of the base form of the indicator. So that means it's on the right side of this color chart right here. So for phenolphthalein, there'll be the pink color, and then for methyl orange, there'll be the yellow color, okay? So the ratio itself could be calculated using the same exact equation that you've seen before, which is the Henderson-Hasselbalch equation for buffer. But now we're going to apply it to that indicator pH and ratio calculation. So if we start with the Henderson-Hasselbalch form of the equation, which is pH equals pKa plus the log of IN minus, the base form of the indicator, over HIN, the acidic form of the indicator, we can solve for this ratio, and that would just be 10 to the power of pH minus pKa. Keep in mind this pKa refers to the Ka of the indicator. Remember, the indicator is just a weak acid that exists along with its conjugate base. So here we have the pKa of phenolphthalein is given as 9.5. They're asking us what the ratio of IN minus to HIN is, and from there we can also tell what color they're going to have, right? If our pH is equal to 5, then the ratio of IN minus to HIN is just going to be 10 to the power of 5 minus pKa, and that ends up being 3.16 times 10 to the minus 5. Again, anytime the number is less than 0.1, then the color you'll see is the color of HIN. Anytime the number is bigger or equal to 10, then you'll see the color of the IN minus. In this case, the number is 10 to the minus 5, which is smaller than 0.1. So therefore, the color we'll see is the color of HIN, okay? And what is the color of HIN for phenolphthalein? It'll be colorless. So you will say, I'll see a colorless solution. I can apply this with, say, pH 12, same exact calculation. So the IN minus to HIN will be 10 to the power of 12 minus 9.5, about 316, which of course is greater than 10. And so the color you'll see is the color of the IN minus. For phenolphthalein, that's pink, okay? So at pH 5, we'll see colorless. At pH 12, we'll see pink, okay? What about pH 9? Well, you can plug that in, place this with 9 instead of 12, and you get that the color is going to be light pink. And that's because the ratio of the IN minus and HIN is just less than 10, but greater than 1. So it's a situation where both the conjugate base and the acid exist of the indicator. So therefore, we're going to have a color that's a mixture of the two colors. So let's talk a little bit about how to choose the correct acid-base indicator now that we know what color will show up at certain pH for the indicator. In a region where the color of the indicator doesn't change, then at that point, of course, it's not going to serve your purpose to help you determine that you've reached the equivalence point. So for example, if your equivalence point, we just look at phenolphthalein right here, okay, so remember that from here to here, phenolphthalein is colorless, and then from here to here, phenolphthalein is pink. So the sensitive part of phenolphthalein is right here in that pH of around 8 to about 10.5 or so, okay? So it's really not helpful if you're trying to use phenolphthalein to detect an equivalence point that happens at pH, let's say around here, right? pH 4. Because at pH 4, phenolphthalein is going to be colorless, whether you're before 4 or after 4. So you're not going to be able to tell just by looking at the color that you've reached your equivalence point. So you have to pick something where the color change happens around pH 4, and that could be bromophenol blue, that could be methyl orange. That's the idea of picking an indicator, is you want to pick something that's sensitive to the equivalence point pH so that you see the color change exactly at that pH, okay? Generally speaking, what we want is an indicator where its pKa is plus minus 1 away from the equivalence point pH. So let's say I'm trying to find an indicator for a titration where the equivalence point is at pH equals 5. Then that means that I want to find an indicator whose pKa is between 4 to 6, right? That's plus minus 1 from 5. You also want to think about the type of titration that you're doing. Strong titration allows for a much larger choice of indicator compared to weak strong titration. The main reason for this is because in a strong titration, that change in pH is very, very steep, okay? So the green plot right here is showing you a strong titration of HCl with NaOH, and you can see that this portion of the plot has a huge change in pH, so the y-axis value changes by a lot, even though the x-axis value changes only by a little. Remember what you're doing in a titration. You're adding titrant from your burette into your flask. That steep increase is telling you that adding a small amount of volume causes the pH to change by a lot. The reason why that's useful for us in picking indicators is as follows. So let's take a look at the strong titration curve. And then what I want to do is I want to pick these two indicators that I've mentioned a few times now, methyl orange and phenolphthalein, and I want to see what color do I observe at different points in the titration. All I'm caring about right now is just the points that are really, really close to the equivalence points, because again, my goal is to detect the equivalence point by looking at the color. So the equivalence point happens at 25 milliliter. I want to know what the color of these two indicators are. Will they be able to tell me that I've reached my equivalence point? Well, let's take a look. At 24 milliliter, what is the pH? Well, we can just use this plot. 24 milliliters right here. So we can just draw a line all the way to the top here and then see where it intersects with the green plot. So the pH is at about 2.5. If you go to 24.5, that intersects around 3. Now, why do I make this half a milliliter jump in my volume of NaOH? Because depending on how you adjust your burette, it's the volume that you're going to add into your flask every time you add the NaOH during a titration. So in other words, the pH doesn't really change by a whole lot. But what happens when I add a couple of drops into my flask so that now I'm at the equivalence point? All of a sudden, my pH is 7, because remember, that's always true for any strong titration. And what happens if I add another couple of drops to 25.5? Now my pH is all of a sudden at 11, right? And then if I go 26, now it's about 11.5. So let's go back and look at this chart for the color to try to figure out what the color of one of the indicators would look like. So again, we're focusing on specifically methyl orange and phenolphthalein. So the pH that we care about is 2.5, 3, 7, and then 11, then 11.5. So at 2.5 and 3, the color of methyl orange is the same. It's basically still going to be just red, right? Because 3 is right here. So anything below that is just red. The color at 11 is all the way up here, and that's going to be yellow. What about the color at 7? Well, 7 is all the way here, so the color is yellow. But the point is, will methyl orange tell me that I've reached my equivalence point? In other words, will methyl orange tell me when I reach pH 7 that the color will change at the same time? And the answer is yes. Because look at this, the color is red, red, and then you add a couple of drops. And I made a mistake here. This should all say yellow instead of orange. So you know at that point you have to stop because you've reached the equivalence point. So in other words, methyl orange is a good indicator to use for this particular titration, even though the actual change of color occur pretty far away from the equivalence point of 7. Right? Let's look at phenolphthalein. What is the color of phenolphthalein at pH 2.5, 3, and 7? You notice that all of those numbers is right here, which is way before phenolphthalein will change color. So all the color here is going to be colorless, okay? There's not going to be any change in color. But when you go to 11, which is the next drop added, now you're at this point, so the color is pink. Then when you go to 11.5, the color is also pink. Now, will phenolphthalein be a good choice for my indicator? The answer is also yes. Why is that? Look, the color is colorless, colorless, and colorless up till 7. But then when you add another drop, the color turns to pink. So will you find out when you've reached the equivalence point? The answer is yes, because phenolphthalein turns at the time when we've added another drop. So we'll go past a little bit of the equivalence point, but it's such a small drop that it's within the experimental area that we can tolerate. So in other words, for strong titration, both methyl orange and phenolphthalein work as well for determining the equivalence point just by looking at the change in color. Okay, hopefully that idea makes sense to you. Now, let's take a look at the weak strong titration. The equivalence point is not 7 now. The equivalence point is actually 8.7. So this is now the blue curve, okay? So the equivalence point is here now. This is 8.7. I'm going to use exactly the same analysis that I just did with the strong titration. So I'm going to look at these 5 volume for the weak strong titration. I want to see what pH do I have. So again, now you have to find the intersection of each of those volume with the blue plot, okay? Not with the green plot, but the blue plot. So you find the pH are 6, 6.5, 8.7, 11, and 11.5, okay? Let's check methyl orange, see if we can see any kind of color change that occurs right around the equivalence point. It turns out that methyl orange just have an orange color all throughout, because methyl orange has an orange color after, methyl orange has a, I should say that should have yellow color instead of orange color, but methyl orange has a yellow color any point after 4.5. So all those pHs that I was listing there, all of these is going to have the same color. In this case, it should just say yellow for all of them, okay? So they all are going to have the same color of yellow, which means that we can't tell that we've reached the equivalence point if we use methyl orange. What about if we use phenolphthalein? The color at 6 and 6.5 would be colorless. The color at 8.7 would be light pink, and then at higher pHs, it will be pink. So for this titration, phenolphthalein is a good indicator, but not methyl orange. So what this tells you is that strong titration, you have a wider choice of indicator that you can use. Whereas with a weak strong titration, you have to be a lot more specific to that equivalence point pH. So here, I want you to look at both of these plots and then decide what indicators can I use for the titration shown below. So this one right here is a weak strong titration, but basically the change of color has to occur somewhere between this pH right here, right? So it has to go, anything that changes pH around 6 all the way to about 10.5 or 11 will be acceptable. So then that covers a lot of different indicators, starting from, say, methyl red all the way to alizarin yellow would work. So basically a list of 7 or 8 indicators there, right? When you look at the second plot, the change in the equivalence point happens at a much narrower range, around pH 8 to about pH 11. So then that knocks down the availability of indicator that you can use. So it's really just these last 3 that would work, which is phenolphthalein, thymolphthalein, and alizarin yellow. So you can see how the type of titration that you have and the plot of the titration really affect the number of indicators you can use to detect the equivalence point for your titration.